Good evening. Welcome to this live session on hydraulic engineering. So today's session is mainly based on the topics of pipe flow, both laminar flow as well as turbulent flow. Okay. So we'll be basically discussing about sorry. We'll be discussing about pipe flow in both laminar as well as turbulent regimes. So this is what is about today's session. So we'll directly come to the questions. So the first question is you have to prove that for a continuous function phi, which is a continuous function of xi, you have to prove that if you uh, the time average of this integral is equal to the right hand side given by this. Okay, so you have to prove this. So how will you uh, proceed? In order to proceed with this problem, you should first of all we should revisit the concept of time averaging. So let us say time average property of any parameter a. Okay, so a can be decomposed into time average components plus the fluctuating component. So what is this time average component? This time average component is 1 by t integration from 0 to t, means for a particular time period, a dt. Okay, so this is the basic definition. Or this can be also written as, say our time interval is from, say the length of the time interval is say capital T. Okay, the length of the time interval. So t minus t to t plus t. So what is the length of this interval? The length of this interval is t plus t minus t plus t. Okay, so twice t. So sorry, so for a time interval of twice t. So basically this particular t and this t means this t basically signifies the length of the time interval. Okay, and then you have to integrate from the lower limit of the time to the upper limit of the time. Okay, lower limit to the upper limit. Now what is this time interval? Actually this time interval is basically one time period. Okay, so if you consider a sinusoidal wave, this t represents one time period. Okay, so that is the thing. So with this concept, let us try to look at the solution. Okay, so if we start with the left hand side of the problem, that is time average of t minus t by 2 to t plus t by 2. So for this case, what is the total time interval? The total time interval is t. Okay, the total time interval is t. So the time average of this entire integral is equal to what? Okay, so our expression is this. Sorry, integration t minus t by 2 to t plus t by 2 phi, which is a function of xi, and the time average of this total. Okay, so time average of any quantity is 1 by the length of the time interval. So the length of the time interval here is what? T plus t by 2 minus t minus t by 2. So effectively you are left with t, because this t by 2 and this t by 2 will get added. So 1 by t. Okay, 1 by t. So see, you are finding the average. Now this entire integral, okay, this entire integral is suppose our a. Okay, that parameter. So 1 by t. Okay, 1 by t integration from t minus t by 2 to t plus t by 2. Okay, a. So a dt, right? A dt. So what is a? A is this entire quantity. So it will be integration from t minus t by 2 to t plus t by 2 phi d xi. So this is our quantity. Sorry. So this is our quantity multiply with a dt. Okay. So this is what is written here. Okay. This is what is written here. So this is our actual quantity. Okay. And the rest, the remaining part is coming from the definition of the time average component. Okay. So this is our A, basically this from here to here. Now since it is given in the question that phi is a continuous function of xi, then we can change the order of integration. So if you change the order of integration, then what happens, this 1 by t, which is a constant, can be taken inside 1 by t integration of, and then since we have changed the order of integration, means phi dt d xi. So this is mathematically possible only if phi is a continuous function of xi. Okay, if phi is a continuous function of xi, then only we can write like this. So what is this particular expression, this expression from here to here, this basically represents phi average, is not it? 1 by t integration from t minus t by 2 to t plus t by 2 phi dt. This represents what? This represents phi average. Now since this represents phi average, so this can be directly written like this. Okay, so and this is the right hand side which you need to prove. Okay, so this is the first problem. Then let us move to the next problem. There are two reservoirs which are 5.2 km apart and they are connected by a pipeline which consists of pipes of different sets of pipe having different diameters. Okay, so there are two reservoirs 5.2 km apart connected by a pipeline which consists of a 225 mm diameter pipe for the first 1.6 kilometer, and for that particular length, that is 1.6 kilometer, the pipe is sloping at 5.7 meter per kilometer. For the remaining distance, the pipe dia is 150 millimeter, which is laid at a slope of 1.9 meter per kilometer. Okay, which is laid at a slope of 1.9 meter per kilometer. Okay, so the levels of water above the pipe openings in the upper reservoir, the reservoir which is at the upper elevation, is 6 meter and 3.7 meter in the lower reservoir. Okay, if you take the friction coefficient as 0.024 for both the pipes and coefficient of contraction Cc to be 0.6, okay, and then you have to calculate the rate of discharge through this pipeline. Okay, now this is a very important problem because this particular problem involves all the particular points that you need to keep in mind while solving pipe network problems. Okay, so that's why this problem has been taken for this session, because it contains all the important points that you need to keep in mind. Okay, so this is the problem figure. As I have always mentioned, it is always better to draw the problem figure before solving the problem. It helps you in visualizing the physical situation. So this is the upper reservoir. Okay, this is the upper reservoir, this is the lower reservoir. So I'm just writing, say, U for upper reservoir, L for the lower reservoir. Okay, now as mentioned above, these two reservoirs are connected by a pipe network such that there are two pipes. For the first 1.6 kilometer, for the first 1.6 kilometer, the diameter of the pipe is 225 mm and it is sloping at how much? 5.7 meter per kilometer. Okay, so as it moves 1 kilometer, it moves down, it is sloping at 5.7 meter. For the rest or the remaining 3.6 kilometer, okay, the pipe diameter is 150 mm, so it is a different pipe. The pipe diameter is 150 mm and it is sloping at how much? It is sloping at 1.9 meter per kilometer. Okay, so this is the situation, and you have to find the discharge through this pipeline. Okay, so since in the question nothing has been mentioned, so we can safely assume that there is no loss or leakage from this pipeline. So whatever is the discharge in pipe 1 here is same as the discharge in pipe 2 from the continuity equation. But in order to solve this problem, okay, you need to apply all the kinds of losses. Okay, head loss. Okay, so definitely we have to make use of Bernoulli's equation, that is the conservation of energy principle, but with suitable losses. Now losses, we have to include the major losses as well as all the possible minor losses. Everything has to be included. Okay, so let us see. So what is H1 and H2? H1 is basically, see, from here to here this gap is H1, and from here to here this is H2. Okay, so H2 and H1. So how will you calculate H2 and H1? See, it is very simple. It is given that for the first 1.6 kilometer the pipe is sloping down as 5.7 meter per kilometer, and for the rest, the remaining 3.6 kilometer, it is sloping down at 1.9 meter per kilometer. So that data you can directly utilize for calculating the value of H1 and H2. So H1 is basically 5.7 into 1.6, because 1.6 is the total horizontal, 1.6 kilometer is the total horizontal distance. Okay, multiplied with 5.7 meter, that is the sloping. So 9.12 meter, and H2 is, for 3.6 kilometer distance, it is sloping at 1.9 meter per kilometer. So 1.9 into 3.6, so 6.84. Okay, so the next part is you have to determine the length of the pipelines. Okay, so length is basically the slanting length, L1 for pipe 1, L2 for pipe 2. Okay, so L1 will be how much? See, if you look at this particular triangle, okay, if you look at this particular triangle, okay, then this is L1, so it is basically the hypotenuse for this right angle triangle. So square root of 1.6 square plus H1 square will give you L1. Okay, so L1 is 1.6 into 10 to the power 3 is basically 1.6 kilometers. So when multiplied with 10 to the power 3, it becomes meter square, plus 9.12 basically is H1. So it is coming out to be 1.6 kilometer. And the length of the second pipe is 3.6 into 10 to the power 3, because it is 3.6 kilometer square, 6.8. So it is again 3.6 kilometers. See, why this is coming exactly same as the length of the pipeline. See, this particular quantity, the first term, okay, that is the length, the distance, the horizontal distance is in kilometers. So it is very large. Okay, so you have a quantity in the order of 3.6 into 10 to the power 3, and then you are raising it to a power of 2. Okay, so when you are raising it to a power of 2, then you will get 10 to the power 6. So with a quantity as high as 10 to the power 6, when you are adding something like say 6.84, so let us say 7 square, okay, 49. So the final quantity will be very close to 10 to the power 6 only, and therefore it is, these two are almost same. Okay, that is the horizontal, the length of the pipeline and the horizontal distance. Okay, now you have to take 2 points A and B. So A is basically on the free surface of the upper reservoir, B is the water surface elevation or free surface of the lower reservoir. Now if you take these 2 points A and B, and then you apply Bernoulli's equation between these points A and B, then see what are the pressure. It is written P atmosphere by rho g, but atmospheric, see, if you take the gauge scale, then this term is directly 0. Okay, because, or if you take the absolute pressure scale, then these two terms will get cancelled. Okay, so that is the first pressure. Then what else is there? 6, sorry, so next what else is there? 6 plus 9.12. So if you look at point A, okay, at point A, What is the velocity head? Velocity head is what? At point A, what is the total energy? Total energy at point A. What is the total energy at point A? So P atmospheric pressure divided by rho g. Okay, it is there. Okay. Apart from this, you are measuring with respect to C at point A. So P atmospheric by rho g. Okay. Plus 6 is what? This particular head. Okay. This particular head. Then you have 9.12. What is 9.12? 9.12 is H1. Means what you are basically doing is, see, you try to understand this equation. I think it will be better if you have two reservoirs. So this is one reservoir and this is another reservoir. Okay, so you have two reservoirs and you are applying Bernoulli's equation between these 2 points, point A and point B. Okay, now if you apply Bernoulli's equation between these two reservoirs, then excuse me, if you apply Bernoulli's equation between these two reservoirs, then what you are getting? You are getting, see, for point A, it is, say we are taking the absolute scale P atmospheric by rho g. There is no velocity head, that is 0, and then the datum head. So datum head, if you are taking which point you are, see, these 2 points are connected by a pipeline. Okay, and if you consider that exactly the center of the pipeline is the datum. Okay, or still better, if you consider that, see, this particular center, if you consider as the datum, then you have to keep in mind one thing, that this is a slanting pipe. So the position as you move along this pipe, it will change. Okay, so if you take, see, now let me show you. That's why, see, we have to apply Bernoulli's equation between point A and B, taking the horizontal plane through the pipe connection in the lower reservoir. Okay, so this particular line is the datum. Okay, so this particular line is the datum. Okay, so if this is the datum, then what is the datum head? See, pressure head P atmospheric, as I have written P atmospheric by rho g. But if you take Gauss scale, then you can directly take this as 0. Okay, there is no velocity here, so the velocity head is also 0. The only thing that remains at point A is the, what is the datum head. So starting from this line, okay, so this particular horizontal line passing through this point is the datum. So from here to here, what is the value? So this is the total datum head. Okay, so this is the total datum head. So now if you look at the figure, so this particular value is 6 meter plus h1 meter plus h2 meter. Okay, so 6 meter plus h1 is 9.12 plus h2 is 6.84. Okay, so 6 plus, or better if I write in terms of symbols, h1 plus h2 plus 6 meter, because this value from here to here is 6. Okay, this is equal to, again, for this point B, the at pressure head, if you take the Gauss pressure measure, is 0 plus velocity head is 0. Is there any datum head for this? Definitely there will be datum head. What is the datum head? The datum head will be h, the datum head will be how much? See, from here to here 3.7 meter, right? So if this is 3.7 plus there will be some head loss. Okay, HL I am writing, plus there will be some head loss. Now this head loss will have some major components and some minor components. Okay, so that is the meaning of this equation. So the total head loss HF, see why I have not written HF in the problem that we are solving, because it is better if you write HL, because in many books the convention is to write HF for major head loss. Okay, so if you write HL, which means the total head loss, and then it is made up of HF, that is the major head loss, and HM, which are the minor head losses. Okay, but you are free to use your own conventions. So what are the losses? The losses are, see, there will be major losses, but major losses are what? One major loss will be while flowing through pipe 1, and another major loss will be while flowing through pipe 2. Okay, so these are the major losses. The friction losses, basically friction loss for pipe 1, friction loss for pipe 2. We will look at the expressions, but first of all let us identify the losses. Then as the water enters this pipe 1 from this upper reservoir, here at this location there will be a minor loss because of the entrance. So entrance loss to pipe 1. Then as this water moves from pipe 1 to pipe 2 here, see, you can see that there is a reduction in the flow area or constriction in the flow area. So because of that there will be a minor loss. So basically we are getting loss due to sudden sudden contraction at the entrance to pipe 2. Okay, and then as the water gets exited from pipe 2 to lower reservoir B, we have exit loss from pipe 2 to lower reservoir. Okay, so entrance loss is 0.5 v1 square by twice g, where v1 is the velocity in pipe 1, so it is a standard formula. Friction loss or major head loss, what is the formula or which equation do we use? We use Darcy-Weisbach equation, F L v square divided by twice g d. The value of F is given to you in the question. What is the value of F? The value of F that is given to you in the question is 0.024. So F length of the pipeline is 1.6 into 10 to the power 3 FL V square twice G D, because 225 mm dia converted to meter is 0.225. Loss due to sudden contraction, C, coefficient of contraction was given to you. So it is 1 by Cc minus 1 whole square V2 square by twice G. Again a standard formula. Similarly we have friction loss for pipe 2, and for exit loss we do not so this directly use the velocity head. Why? Because exit loss is similar to a minor loss due to sudden expansion, where the larger area is infinity. So that's why you are getting this equation. So next what you can do is, see, in this particular equation, see, after you have substituted these things here, you will be getting this. Okay, you will be getting this equation 18.26, but here you can see that there are two unknowns, v1 and v2, but this is not a problem because you can convert v1 and v2 with respect to one another. How? Because the discharge q can be written as a1 v1 equal to a2 v2. A1 and A2 are known to you because you know the diameter of the pipes. So either V1 can be written as A2 V2 by A1, or V2 can be written as A1 V1 by A2. So you can do either of the one, and based on this you can substitute in this equation and you can get the value of V1. And once you have the value, or you can directly see, you can substitute in terms of Q also, that is your wish, but this is normal algebraic manipulation. Once you know this, you can find the value of discharge, which came out to be 0.0135 meter cube per second. So see, this problem is a very simple problem, but it covers all the losses, okay, all the possible losses that can occur in a pipeline. So that's why this problem is very important. Okay, then the next problem. For the distribution main of a city water supply, a 36 centimeter diameter pipe is required. Okay. As pipes above 30 centimeter are not available, it is decided to lay two parallel mains of the same diameter. Assuming the friction factor of all the pipes to be same, determine the diameter of the parallel main. So basically it has been found that in order to supply water for a water distribution network of a city, the diameter of the pipe should be 36 centimeter, but there is a restriction. The available pipe diameters in the market is only 30 centimeter. So it was decided that if we provide two parallel main lines, okay, of 30 centimeter diameter, okay, and if you assume that the friction factor F is same for all the pipes, we have to determine the diameter of the parallel mains. Means what should be the diameter of the parallel mains, okay. So how do you solve this problem? Let suffix 1 or subscript 1 denote the 36 centimeter diameter pipe, and suffix E denotes the equivalent pipe. Okay, we have to, basically it is a equivalent pipe problem. Means one single pipe of 36 centimeter dia is replaced by two equivalent pipes. Okay. Now, if it is parallel pipeline system, then what happens? The major head loss is same. So F1 L1 V1 square by twice GD1 is equal to FELE V square equal to twice twice GD. In the present case, see, the length we are not changing. L1 is equal to LE, and also it is given in the question that the friction factor of the pipes remains unchanged. That is F1 equal to FE. So therefore V1 square by D1 is equal to V square by D. Also, okay. And then from continuity equation, see, continuity equation, what happens? So there is a main line, okay. So this total discharge is now, see, for the actual 36 centimeter dia main pipeline, the total discharge is now getting divided into two pipes. So whatever discharge was there for this pipe, that is A1 V1, so pi D1 square by 4 into V1 here, is basically distributed into two pipelines. So that's why 2 into pi D square by 4 into VE. Okay. So from this we can get a expression relating V1 with VE. Okay. Now if you substitute this value of V1 in this equation, we will be getting an expression for, an equation where the unknown is DE. Okay, but DE raised to the power 5. Okay, if DE raised to the power 5, we can solve this equation very easily, and we found that the value of D is 27.28 centimeter. So whatever next higher size available, means say 28 centimeter size is available, or maybe 27.5 centimeter size is available, so we can take that. Okay, but you cannot take a lesser size, because if you take a lesser size pipe, then the discharge will be less. Okay, so again this is a very simple problem, and then let's move to the last problem of this session. A hydrodynamically smooth pipe. Now what is a hydrodynamically smooth pipe? A hydrodynamically smooth pipe is a one where the roughness elements lie well within the viscous sublayer, okay, or the roughness do not protrude above the viscous sublayer. So it is a hydrodynamically smooth pipe, and it carries water at a rate of, the discharge is given 300 liters per second at 20 degrees Celsius, and at 20 degrees Celsius the density of water can be taken as 1000 kg per meter cube, and the kinematic viscosity is 10 to the power minus 6 meter square per second. Okay, the head loss is 3 meter in 100 meter length of pipe. You have to determine the pipe diameter. You will have to determine the pipe diameter. Okay, and for friction factor F, you can use this formula. See, since this is turbulent flow, some particular form is given to you, which is a function of Reynolds number. Okay, and you can, since Darcy-Weisbach equation is valid for both laminar as well as turbulent flow, you can use Darcy-Weisbach equation, but the value of F you have to determine from this. Okay, and Reynolds number is basically rho Vd by mu, which you all know. So how will you solve this problem? All of you please take 2 minutes of time and see. Let us look at the solution. So these are the parameters which are given to you. Discharge of 300 liter per second, which when converted to meter cube per second becomes 0.3 meter cube per second. Density of 1000 kg per meter cube. Kinematic viscosity 10 to the power minus 6 meter square per second. Head loss of 3 meter for how much? For a length of 100 meter. and friction factor F is given by this formula. Now you have to determine the diameter of the pipe. So if you use Darcy-Weisbach equation, FL V square by twice GD, so 3, everything is given to you except F and D. Okay, and plus velocity is also not known. So F can be expressed in an expression like this. Okay, F is equal to 0.5886 D by V square. Now what is Q? Q is area into velocity. Area is pi d square by 4 into V. So d square V is 0.382. Then you can find an expression of V is 0.382 by d square. Okay, and the value of F is the expression for F that you can use is given to you. So if you substitute these values, okay, so F is what? 0.58. It's in this particular expression. See, F is equal to 0.5886 d by V square, 0.0032 plus 0.221. Reynolds number is what? Reynolds number is rho V d by mu. Is not it? Rho V d by mu. So rho value is given to you. The value of rho is given to you. V is not known. D is not known, but the value of mu is known. Why? Because the value of nu is known. Nu is what? Nu is mu by rho. So if you substitute all this here and further you can replace this V with 0.382 by d square, you will be getting a highly nonlinear equation in terms of d. Okay, now this equation you can solve either by trial and error, or you can make use of any suitable numerical technique for the solution of nonlinear algebraic equation, and which will give you the value of d as 0.308 meter. So this kind of problems is sometimes is asked in your university exams, and you should have a good practice. Okay, you should know how to solve the nonlinear equation either by trial and error, or maybe you can make use of Newton-Raphson method. Okay, that is the best method, but you should know, you should practice. Okay, so with this let us stop here. We'll again meet next week. Thank you.